Coming to the next module, fourth module, comparatively ചെറുതാണ്, അധികം പഠിക്കാൻ കുറവാണ്. So just relax ചെയ്തിട്ട് പഠിക്കണം. Okay, so we'll start the fourth module and have. So fourth module is all about circular slabs. Okay, the fourth module is we will be studying the design of a spherical dome, conical dome, and that is a small design also. Okay. So first of all, we'll start with a circular slab. So see this. So this, have you seen this? So this is a circular slab. So where are we using circular slabs? So you might have seen the septic tank. Okay, circular septic tank. On the top of it, you will be having an RCC slab, circular shape. Okay, the same time you might also see the water tank, circular water tank. Okay. That is of our water authority in the water tank will be circular in shape. Okay, so you can see the bottom portion, it will be a circular slab. At the same time, top portion will be also having a circular slab. Okay, and also some porches will be made. The houses, the porch of the houses will be made in a circular slabs, and also balconies, porches. All these are examples of circular slab. Okay, so unlike a rectangular slab, the construction and reinforcement of a circular slab is entirely different. Okay, so we have learned about the reinforcement details of a normal rectangular slab, whether it is a rectangular or a square, whatever it is. Okay, so one-way slab and two-way slab, we have learned about the reinforcement. So how we are providing reinforcement? Reinforcement we are providing on the bottom side, then we are providing on the top side. Okay, that's what we are providing for a normal rectangular slab. Coming to a circular slab, so this is how we are providing the reinforcement. Okay, so circular slab mainly we are having two types of reinforcement. First one is circumferential and radial reinforcement, and the second one is the mesh reinforcement. Okay, so you can see there are two types of reinforcement: radial and circumferential reinforcement, and also a mesh reinforcement. So as you can see here, okay, so this radial and circumferential reinforcement will be provided at the edges. You can see, okay, the radial radial circumferential you will be providing the reinforcement at the edges. Okay, coming to the center portion. Okay, near the center, you will provide the reinforcement as a mesh. Okay, in the center portion, you will provide the reinforcement as a mesh, and coming to the edges, you will provide the reinforcement as a circumferential and a radial manner. Okay, so this is the correct picture. Okay, so this is a detailed picture. Okay, so in circular slab, you are providing two types of reinforcement, that is radial and circumferential reinforcement and mesh reinforcement. Okay, so mesh means simply you can see the so mesh means simply you can see this is a mesh. Okay, this is called as a mesh reinforcement. Okay, that is you will be keeping the reinforcement bars in the orthogonal. That is, first you will lay in one direction, on top of it in the opposite direction you will lay the other reinforcement. Okay, so this is the orthotropic mesh reinforcement. You can also call it as mesh reinforcement. Coming to the second one, that is radial and circumferential. You can see this is the radial reinforcement. Okay, one which is radiating outside. From the center, it will be projecting towards the outwards. Okay, from the center portion, the reinforcement will be extending towards the outwards. That is a radial reinforcement. You can see. See here. Circumferential means this round one. This is a circumferential reinforcement. Okay, so for a circular slab, you will combine both this and then you will provide a reinforcement. So how we are providing? That is near the edges, you will provide radial and circumferential reinforcement. Both radial also you will provide, at the same time circumferentially also you will provide reinforcement near the edges. Center portion, how will you provide? You will provide as a mesh. Okay, so this is very important to understand. So come on here. Here you need to study 3 derivations. Okay, 3 derivations you need to study. So you can write down. This is very important also. So first thing is that you need to study about a simply supported circular slab which is uniformly loaded. Okay, so you can write it down. A simply supported circular slab. Okay, a circular slab which is simply supported and the load is uniformly distributed over it. Okay, so can you say an example of this? Okay, so you need to study the derivation about the slab. So here you will find out the radial moment, circumferential moment, and also maximum shear force. In മൂന്ന് കാര്യങ്ങളാണ് നമ്മൾ കണ്ടുപിടിക്കേണ്ടത്. Radial, circumferential moment, പിന്നെ shear force. ഇത് മൂന്ന് സംഭവങ്ങളും എവിടെയാണ് maximum വരുന്നത് നോക്കണം. Okay, so for that yesterday, so simply supported that you might have seen for the water tank. Okay, the water tanks in the top portion. The top portion of the water tank, or you can say the top portion of the water tank, it will be simply supported. See, just like this. Okay, top of the water slab, water tank in the top portion, it will be simply supported. Just ഒരു അടപ്പ് പോലെ ആയിരിക്കും വെക്കുന്നത്. Okay, so that is an example of simply supported circular slab which is uniformly distributed. Okay, so you can draw the figure. Okay, please draw the figure. Mark the center O. Okay, this is the center O. So R is the radius of the slab. Okay, R is the radius of the slab. Okay, and this R is radius at any point. The small r, it is the radius at any point. Okay, so that's R is small radius at any point. Okay, so now we are taking a section over here. So take a section over here. You can see this is a section XS. Okay, so both sides we will have a simply supported. Okay, this is a center O. This is a load W that is uniformly distributed. So this will be your R direction. Okay, so you are taking a section over here. What you can see. Definitely, what is the load? Load, and also this is the radius R. This is also an R. This is also another R. Okay, so you are taking a point P here. Okay, so the point is just a point P and a radius to that point is taken as small r. Radius to that point is taken as small r, and theta is the inclination of the horizontal with this r. Theta is the inclination of the horizontal with this r. Okay. So next, here you need to by heart an equation. First one is this equation you need to by heart. Okay. So that is a radial moment at the point P at a distance of r from the center O. Okay. So the radial moment at this point P. So you have considered a point P over here. Okay. So radial moment at this point. Okay. So since it is circular slab, here you will be having radial moment and circumferential moment. Okay. So here you are having radial moment and circumferential moment, not unlike a rectangular slab. Okay. So first is you have to consider the radial moment at this point P, which is at a distance of r from the center O. So this equation you need to by heart. Mr is equal to 3w divided by 16 r square minus r square. There is no other way. Okay. You don't need to study about the derivation of this. Okay, you can just completely by heart this. So write down 3W divided by 16 R square minus R square. Now, coming to the diagram. So can you just tell me where will you having the maximum moment from this loading diagram? Okay, your loading diagram with it. Can you just tell me where will you have this maximum moment? Train completed. So you have completed the SA1, SA2. So just from that all this information, you can just assume where will you have the maximum moment. Can you tell me what is circular slab maximum on where it will occur? If you take a section over here, can you please tell me? Definitely central. Central ആണ് നമുക്ക് ഏറ്റവും കൂടുതൽ മൊമെന്റ് വരിക. സൈഡിൽ നമുക്ക് മൊമെന്റ് ഉണ്ടോ? ഇല്ല, because it is simply supported. Okay, simply supported ആണ്. This is a simply supported. Okay, simply supported ആയതുകൊണ്ട് end portion you are not having moment. Okay, so maximum moment load വരുന്നത് ഇങ്ങനെയാണ്. എൻ്റെ bending ഇങ്ങനെയായിരിക്കും വരിക. So this is how it will bend, right? Okay, since the bending is like this, you can expect the maximum moment at the center. So we can write out this MR will give the maximum value at the center. Okay, the radial moment will give the maximum value at the center. At the center, R is equal to 0. So this is the origin. This is a start point. Okay, so center we are getting the maximum value means at the origin R is equal to 0. So you can substitute R is equal to 0 in this equation. Okay, so substituting R is equal to 0, radial moment is equal to 3W divided by 16 R square. So this R, this mole R is equal to 0. Only you will be having this 3W 16 into R square. Okay. Okay, now coming to the circumferential moment. So this is the equation. Again, you have to study this equation. Circumferential moment for a simply supported slab having uniformly distributed load is m theta is equal to W by 16 3R square minus R square. So I cannot help it. You have to study this equation. So W by 16 3R square minus R square. You can write on the equation. Okay. Just hold on 1 second. Okay, so please write down this. So circumferential moment is equal to, this is the equation. For circumferential moment, we can say the maximum, where will be the maximum moment? Okay, first on this diagram we can understand anyway the maximum moment will be at the center. Well, you will have the maximum moment at the center. Why? Because it will, anyhow it will be bending like this. The bending will be like this. Okay, the parabolic at the bending at all. Okay, so circumferential moment we can come to a conclusion that maximum moment will occur only at the center. So in the center you can say r is equal to 0 because it is the origin point. See here, this is the origin point. R is equal to 0. The small r is equal to 0. Okay, so you can substitute r is equal to 0 here. Okay, you can substitute r is equal to 0 here. So you'll get the equation as maximum moment. Maximum circumferential moment is equal to 3w r square divided by 60. Okay. Okay. Now, since it is a circumferential moment, see this is a circular slab. Imagine this is a circular slab, and this is how you are providing a circumferential reinforcement. Okay. So this moment is arising circumferentially, along the radius. Circumferentially you are having a moment. Okay, because of this bending you can see from this diagram. See, so you can see in this diagram the bars has been circumferentially aligned. Circumferential നമ്മൾ bar bend ചെയ്താണ് കൊടുത്തിരിക്കുന്നത്. Why? Because there you are having a circumferential moment because of this geometry. A circular ന്റെ ആ ഒരു geometry കാരണം you will be having a circumferential moment at the support. Okay, so unlike the rectangular slab or circular slab, see, because of its geometry, edges you will be having a tensile stress. Okay, on the edges you will be having a tensile stress, and thereby there will be a circumferential moment at the edges also. Okay, so you have to consider the circumferential moment at the supports also. Okay, so for circular slab, you have to consider the circumferential movement at the edges also because why? Why? Because at the edge you can see this edge portion. But there will be tensile forces will be developing. The tensile force will developing on the there. That's why we are providing a circumferential movement over there. Okay, so that circumferential movement you have to consider. Okay, so circumferential movement. How to find out the circumferential movement? Okay, so circumferential movement that is occurring at the edges. So here at the edges, the small r is equal to large R. Is it? You can see from this figure. This is here you are having a circumferential moment. Okay, so here the radius is here the R is equal to R. Okay, so substitute in this equation ER in the second case we can substitute this small r is equal to large R. So to find out the circumferential moment at the supports, you can substitute this R, small r is equal to R. Okay, so you'll get the answer like this: m theta is equal to 2w r square divided by 60. Okay. Next is you have to find out the radial shear force. Okay, so unlike the rectangular slab, now we are developing the radial shear force. That means the shear force is developing radially in the radial directions. Okay, that is radial like this. Okay, this is how it is developing. Okay, so here you are having a radial shear force. Okay, so radial shear force in the equation is 1 by 2 W by R, or is equal to, or you can say 0.5 WR. So radial shear force at any point. Okay, so we can say a regular point. If you take any point at this point like this, see, suppose this is the point P. Okay, so radial moment at this point. Okay, the radial shear force at this point is equal to 1 by 2 WR, or 0.5 WR. Now, where will the radial, every day become shear force maximum? Where will you have the maximum shear force? Can you please tell me? So you can always tell. Maximum shear force always occurs at the supports. Supports line you will be always having the maximum shear force. The maximum shear force, whether it is for a rectangular slab or rectangular beam, wherever it is, the maximum shear force will be always occurring at the supports. Why? Can you please tell me why? Why? Because you can see here, this is the support. Okay, this is the support. This is the support, and this is how the slab will be. Okay, okay, this is how the slab will be. Okay, so this is where the shear force is developing. Okay, ഈ supports ആയിരിക്കും. Shear force means what? That's a tangential force. Okay, support means the shear force means that the tangential or equal and opposite forces that is developing. Okay, so this forces will be more developing in the supports. ഇവിടെയല്ല നമുക്ക് ഇങ്ങനെ tangential ആയിട്ടുള്ള force develop ചെയ്യാനുള്ള chance കൂടുതൽ. See, there's a chance that ഈ beam ഇതിന് detach ചെയ്യാനുള്ളത്. That's why you're having a maximum shear force at the supports. Okay, so you'll be always having the maximum shear force at the supports. So you can again substitute this equation, R is equal to R. Okay, so the supports, the small r will be equal to large R. So you can say R is equal to R, you will get the maximum shear force, maximum radial shear force. So that is equal to, substituting the small r is equal to large R. Why? Because the radial shear force will be always maximum at the support. Okay, so the supports you'll be having the maximum here, you'll be having the maximum radial shear force. So here the R is equal to R. Okay, so substituting this equation you will get WR by 2. WR by 2. So similar way, we can see what will happen if the slab is having a fixed end. Okay, so just we go to next step. So similar way, we can see what will happen if the slab is having a fixed. The slab is having a fixed support and it is having a uniformly distributed load. Okay, so you can write on the second case, that is a fixed circular slab which is having a uniformly distributed load over it. Okay, so same thing, you can take a point R over here. Okay, any point, sorry, you can take a point P at a distance of R from the center. R is the radius. You can take a section over here. The section will be like this. Okay, so this is the same way. Okay, so here also you have to by heart this equation, that is the radial moment at the P is equal to W by 16 R square minus 3 R square. So this equation you have to by heart. Simply supporting the equation is different. So simply supporting the equation was something like W by 16 3 R square minus R square. So here it is W by 16 R square minus 3 R square, small 3 R square. Okay, so difference is that. So radial moment is equal to W by 16 R square minus 3 R square. Okay, now we will be having the maximum moment. Or will have the maximum moment. So similarly, here also we can say that the maximum moment will be occurring at the center. Okay. So here it is you are having positive moment, negative moment. So neglected. You can say that the maximum moment is occurring at the center where R is equal to 0. So here the R is equal to 0. Okay. So here the R is equal to 0. At the center R is equal to 0. So if we substitute in this equation R is equal to 0. Okay. So in the first case, to find out the maximum moment, you can substitute this R is equal to 0. You will get how much? What will you get? No, this you will get this equation. So maximum moment at the center is equal to W R square divided by 60. Okay. Even the case fixed also, you are getting the maximum moment at the center. Central arc maximum moment is W R square by 60. And other supports. Okay, so here you are having negative moment and positive, that is sagging and hogging. Okay, sagging and hogging moment. Okay, so here negative other supports also fixed support moment in the simply support at least supports you are not having moment. Moment is 0, but in case of a fixed moment even if it is small, you will be have a fixed maximum will be always at the center, but at the supports also there will be moment. Moment is support down, but the maximum maximum always you will get in the center in case of a fixed. Okay, so here at the supports also you are having moment. Okay, so the support moment you have to substitute R is equal to R. That is, if you substitute R, small r is equal to big R, you will get how much you will get? Minus W R square divided by 60. So this equation, the same equation, you can substitute R is equal to R to find out the moment at the support. The same equation you should substitute R is equal to big R to find out the moment at the supports. Okay. Why? Because this is a fixed support. Fixed support supports moment maximum moment you will get in the center, but at the supports also you are having moment. Now coming to the second one, that is circumferential moment. Same equation, not same equation, different equation, but you have to by heart this equation. M theta is equal to W by 16 R square minus R square. This is the equation. Okay, so substitute this again, take this equation. So here also same way, circumferential moment will be maximum at the center. So maximum at the center means what is center and then R is equal to 0. You have to substitute R is equal to 0. R is equal to 0. Okay. So circumferential moment, maximum moment will be developing at the center. The center, that is the origin point. You can say small r is equal to 0. And at the supports also there will be some kind of moment. So you have to find out that also. So to find out the support circumferential moment at the supports, you have to substitute this small r is equal to big R. Okay, to find out the circumferential moment at the supports, you have to substitute small r is equal to big R. So in the sum we can do R square will be equal to 0. So you will get the circumferential moment at the supports as 0 for the fixed case. Okay, so for the fixed circular slab, circumferential moment at the supports will be 0. Okay. Now next one, last one. Oh no, no. Now you have to consider shear force also. Sorry. Same equations. Okay, radial shear force. So shear force is equal to 1 by 2 WR. So maximum shear force will be always at the support. There is no doubt about it. So at the support, small r will be equally larger. That is 1 by 2 WR or 0.5 WR. Same way. Okay. Okay. Now coming to the third case, that is partially fixed. So this is actually intermediate case, that is partially fixed and partially simply supported. So this is an intermediate case between the fixed slab and the simply supported slab. Okay, so same, that's the third case. So I'll show you an example next class. So just now you can write it down. So this is a partially fixed circular slab which is having a uniformly distributed load over it. Okay, so here the same way, this is a radial moment. Radial moment is equal to W by 16 2r square minus 3r square. Okay, so again the moment at the center, that is the maximum moment at the center you will get when you substitute this r is equal to 0. So 0, so you will get the radial moment at the center as 2wr square divided by 16, and also to find out the moment at the edges. Moment at the edges, you can substitute this r is equal to r. Same, the same method. That is, you have to find out the moment at the center, and also you have to find out the moment at the edges. So center you have to substitute the small r is equal to 0, and to find out the moment at the edges you have to substitute small r is equal to big R. Same thing. So you will get this equation. You can write it down. Now come into the circumferential moment. Okay, circumferential moment, this is the equation. M theta is equal to W by 16 2r square minus r square. Okay, so this is the equation. W by 16 2r square minus r square. So same way you have to find out moment at the center and also moment at the support. So moment at the center is equal to r is equal to 0. Moment at the support means r is equal to big R. Okay, so you'll get this equation. You will get this equation at the center, at the edges. Next is you have to find out the shear force. Okay, shear force, same equation. 1 by 2 WR or 0.5 WR. Okay, so maximum shear force always occurs at the supports. So you can substitute this R is equal to BR. You will get the maximum shear force as 0.5 WR. So that's it. You can write down. So this is a simple derivation. All you have to do is that you have to just by heart all these moments. Okay. Okay, just write down it, and you can pause your names to mark the attendance. You can pause your names to mark the attendance. So this portion I will upload in Language today itself. So if you want to write down, you can just write down today. Write down this derivations. Tomorrow we'll start the problem. It's a simple problem, small problem, nothing to worry about this. Okay. So please, all of you, please post your names to mark the attendance. Okay. Okay, just write down it and exit.